So beginning chapter 15, our first of two chapters that cover the sun. This chapter focuses on the characteristics and features of the sun, as well as the way the sun interacts with the solar system. Chapter 16 is all about what happens inside of the sun, mainly fusion. So let's give an overview of the composition of the sun. And why do we bother studying the sun? Well, because it's close. It's a great opportunity to study a star in our back door. So what is the composition of the sun? So the sun has mostly in terms of percentage of atoms. So if you were going to go and count all the atoms, which obviously scientists don't do, but they have reliable mechanisms based off of spectra and particular phenomenon where they're able to derive these percentages. And so the percentage of atoms that make up the sun that are hydrogen is 92. In other words, most of the atoms inside the sun are hydrogen atoms. And remember that a typical hydrogen atom is just one proton. It's only the quite rare isotope called deuterium that has one proton and one neutron. 7.8% of the sun is composed of helium. All right. And I said percent of the sun, which is kind of weird. What do I mean? Mass? No, atoms. Okay. So 7.8% of the atoms in the sun are helium atoms. And these are your 2 proton, 2 neutron helium atoms. All right, so in the nucleus of helium, 2 protons, 2 neutrons. In comparison to other stars, how does the sun compare? Well, it's got less hydrogen and more helium than these other nearby or large stars. Alpha Draco, Omega Pegasus, Vega, Theta Leo. Quick note on the naming because it's quite fascinating and I think you might be interested in it as well. The naming convention refers to the constellation where the star is found. And the first word is just the brightness of that star in that constellation. So for example, Alpha Draco is the brightest star in the Draco constellation, which if you haven't heard of it, yes, it is a real constellation. Theta, being the, not sure, maybe 9th letter in the Greek alphabet, tells us that Theta Leo is the 9th brightest star in the Leo constellation. And we all know that constellation. Vega doesn't follow that naming convention because it's such a bright star that it has its own unique name. That's true for a few other stars like Polaris, Betelgeuse, and so on. But why less hydrogen? Well, maybe because of the type of star that we have, maybe because of the phase of life that our sun is in. These are all things that we'll talk about when we talk about comparing stars in future chapters. Although it certainly does seem reasonable that there's more helium and less nitrogen together. What I mean by that is that these two values should be related to each other. And we will talk about that in chapter 16. Suffice to say for now, the sun burns hydrogen, not literally, but that term gets colloquially used, into helium. What it really does is it fuses hydrogen into helium. So to compare that to the primordial atmosphere, the first atmosphere of Earth, we can see that there is indeed less hydrogen in the sun than there is theorized to have been in the original solar system. Because remember, the earliest atmosphere was the atmosphere that was shared by all of the planets. They all started with that same primary atmosphere because that was the atmosphere of the disk that formed the whole solar system. And indeed, more hydrogen, less helium, because the sun has been changing those numbers in the last 4.5 billion years. That's how it remains bright and hot. Compare that to the current atmosphere of Jupiter, and we see that same trend continue. We see Jupiter has more hydrogen, even more hydrogen than the earliest atmosphere. So in terms of comparisons, Jupiter's atmosphere, the most hydrogen. Early atmosphere, less, but still more than the current amount of hydrogen in the sun. So why is that? Well, Jupiter doesn't burn hydrogen. Jupiter's not a star. Instead, Jupiter's a gas giant. What it's done with hydrogen is essentially collected it. So the fact that Jupiter has more hydrogen than the disk that formed the solar system had, so more than everything started with, makes sense because it's been consolidated, concentrated in this gas giant. And none of it has changed. It can't go anywhere. Even with things like metallic hydrogen and those high pressures that we talked about when we talked about Jupiter's core, those were not the same level of energy that actually can cause elements to change from one element to another, because that process is called a nuclear process, and that requires even more energy than you'd find inside of Jupiter. That requires the kind of energy you find inside of a star. All right, so no fusion inside of Jupiter. And this is just pointing out the where some of the carbon and nitrogen went into the methane and ammonia. So thinking about that as a nice segue, right? Going back to those molecules that we talked about when we talked about the gas giants, and even more when we talked about the so-called ice giants of Neptune and Uranus. So lots of molecules, right? CH4, NH3, methane and ammonia. Well, we don't see molecules in the sun. Why? Why are there no molecules in the sun? At least hardly any. What do you think it is? Too cold, too hot, too young, too old? They've all broken down? What is it? All right. I have a vote for two. Anybody else? Thank you, Maxwell. All right. I think that is a consensus and is totally reasonable, right? So what I was thinking that, that would probably seem, like not the most difficult question. And I'm glad it didn't. It's just too hot. They're going to get disassociated, which we talked about Venus. Okay. Sun just can't support those molecules. The bonds get broken. So if we look at elements in the sun in terms of abundance, this would just be another way of expressing it. Just think of this as a little bit of a mathematical aside. So it's not telling us anything new, but it's pointing out that if you want to talk about percentages, right? Well, the percentages sum up to 100. So you look at that 92 and you in your mind you think, okay, well that's 92 over 100. And that's a great way to think about relative amounts of something. Another way is to have a ratio. It's all, essentially a fraction, but we often call them ratios. And in that case, well, for every one hydrogen atom, right? So, how many, so how many do you have, or actually in this case, how many hydrogen atoms do you have for one of all the other atoms? So this is even a kind of an unusual way of doing ratios because it's just always comparing to hydrogen. And so the way we would read this is, it's still a ratio, is that we'd say, okay, well, for every one helium atom, you have 12 hydrogen atoms. And that also is a great way to visualize and conceptualize numbers. Do it one more time. For every one carbon atom inside the sun, you have 4,600 hydrogen atoms. For every one nitrogen, you have 11,500 hydrogen atoms. What makes this way of talking about atoms even more relevant to a discussion of a star is because the processes, if you looked at the most recent homework 7, involve individual atoms. And if you want to think about how fusion rates can proceed and how they might be inhibited or bolstered by ratios like this, actually thinking about the atoms in the sense as one handful compared to another instead of just more ambiguous percentages is really the way to do it because you are thinking on that scale of individual atoms. And then going back to percentage of mass, so in that, not back to mass, but referencing mass, which I had hinted at before, you notice a disparity between the percentages. So now ignore this whole ratio thing. We've talked about it, we're done. Now I want us to think percentages again and just notice that although there are 92% of the atoms inside the sun that are hydrogen, I always start that sentence in a way that makes it harder to finish, but you get the idea, right? 92% of the atoms are hydrogen atoms. Well, only 73.4% of the sun's mass comes from hydrogen. Why such a big difference? Okay. Why is it, why is it that you can have 92% of the things that build the sun, but yet have them only reach that 73, Well, it all comes down to, and this is a looking at the mass of, so looking at the mass of each atom. So here's your answer. To sum it up, let's see. So go check what something, Excuse me there. Just want to make sure. So even though it's most of the atoms, each one only has an atomic mass of 1. Hey, fun reminder. That's one what? Well, that's 1 atomic mass unit. So atomic mass unit, right? And remember that is 1.67 times 10 to the negative 27 kilograms. We see that in the homework, for example. When you want to convert mass to energy. And we saw it back with atmospheric retention as well. So there you go. That's the way that we talk about really small masses, right? Because we don't want to always refer to them in kilograms and scientific notation. So instead we talk about AMUs, which sometimes is just shortened to just U, and hydrogen is just one of them, okay? And it's not exactly 1. Once we include like 6 significant figures, we see that it's not exactly 1. In fact, carbon is the standard. Carbon is precisely 12, and that's how the whole system of AMUs is derived, right? It's that, carbon is that comparison, and it's defined as exactly 12. Okay, but that's the reason right there. That's the reason that the percentage of mass can be so low for such a high percentage of atoms, because each hydrogen is so light, has so little mass to it, right? Helium's 4 times more massive. Every single atom is. Carbon's 12 times more massive. And so then this last column here is just looking at the, remember. No, 9231. Oh, it's forming the percentage of mass. And that's not, I guess it's just not the same as the helium. Huh. I'll have to look into that. Don't worry about it for now. Just focus on these 2 columns. And this one as a good reference to some physics, nuclear physics. Okay. So enough for our basic characteristics. At least what have we talked about so far? Just what the sun is made out of. What have we really seen? Mostly hydrogen, right? A little bit of helium. And namely less hydrogen and helium than it started with, or at least implied by the primary atmosphere comparison. Now, let's look at some of the characteristics that we did for planets, such as the size, density, and so on. All right. So the sun has a radius of 700,000 kilometers. That's over 100 times bigger than the radius of Earth. Okay, which I think is, so it's not right here. It may come up. I seem to remember it, but if I'll put it here at the risk of it being repeated. But the radius of the Earth is 6,370. So I'll approximate it as, we'll say, 6,500 as a rough approximation for kilometers. And then if we round that even more up to 7,000 kilometers, then we see that the sun is 100 times bigger, or we could just confidently say over 100 times bigger across than Earth. It would take 100 Earths lined up, right? That's to be smaller than this to get all the way across the sun. The mass of the sun is 2 times 10 to the 30 kilograms, which is 330,000 times the mass of Earth. Even though it's only 100 times wider, it's way more massive. And that's because of that cubic relationship between volume and radius, and the fact that volume is directly proportional to mass. Okay? I know idea we keep going back to, but it's crucial to so much understanding when it comes to astronomy. The density is fairly low at 1.4 grams per cubic centimeter. It is comparable to gas giants, a little bit heavier than or denser than Saturn, but not as dense as some of the gas giants, and way less dense than a terrestrial planet. All right, so it's got a lot of relatively low density gas. The temperature, and when we talk about temperature, we're talking about the surface temperature, is 5,800 Kelvin. Okay, and the surface temperature, well, might be confusing because, wait, does it have a surface? No, not really. But it does have something called the photosphere. That is just the part of the sun where it becomes opaque to our eye, to the visible spectrum, okay? And to most spectra for that matter, at some point, right, it becomes too dense. But you could pierce deeper into the sun with radar waves, for example, radio waves, that process being called radar. Regardless, the surface of the sun is what we talk about when we talk about the temperature. And maybe the best way to remember that is just to think, well, why do we even care so much about temperature? We care about it because we can relate it to color with Wien's law, which was that black body radiation law that let us say, hey, if you know the color of something, then you can calculate its temperature, or vice versa. All right. So which part of the sun has the temperature of 5,800 Kelvin? Sorry, I already gave it away. It's the photosphere, okay? It's what is the stand-in for the surface. It's not solid, you can't stand on it. You would definitely sink in it, but you wouldn't make it there anyway because 5,800 is really hot and you would burn up. But it is that part that is the visible boundary of the sun, the photosphere. Okay, the interior is underneath it. We'll talk about that a bit. The atmosphere, no surprise, is above the photosphere. So it's almost like what we talked about when we talked about gas giants, when we said, the cloud layers, the bands of clouds, all of that was that, that visible part of the gas giants, which we kind of it's easy to think of that as the quote unquote surface. Same thing here, but it has a special name. It's called the photosphere. So let's work our way out from the center of the sun, quickly going over the layers. We'll get more into what happens inside of the sun in chapter 16. So at the very center is the core, same term that we use for terrestrial planets and gas giants, right? The core is always just the center. All right, this is where fusion takes place. More on that later. High energy gamma ray photons are generated. Okay, so the reason this is mentioned is because we're going to be interested in the path of light from the core to the photosphere. And that's because we care about the mechanisms, as well as, of course, the fact that the light is really part and parcel with the energy. It's the very nature of the sun. The sun makes energy, right? It's a source of energy. That energy is heat. The heat is light. They're totally interchangeable. And one big reason is because once the heat makes it to space, the only way that heat can move through space is through electromagnetic radiation. The other two mechanisms of heat flow, conduction and convection, don't work in the vacuum of space. They simply don't apply. So radiation, those EM waves, are the only way to go from point A to point B, to go from the sun out into space, reaching the planets, reaching the outer solar system, reaching other solar systems where the sun is just a dot in the sky. Okay, the temperature of the core is about 10 million Kelvin. All right, that number will become important when we talk about fusion. It's the necessary temperature for the type of fusion that occurs inside the sun. The density is very dense. It's denser than gold. So even though the sun as a whole is low density, the core is very high density. Okay, and so we're talking, about 10 times denser than gold, and gold is over 10 times denser than water. So 100 times denser than water. This is super dense material. The type of thing that does not exist on a macroscopic level on Earth, can only be created in labs. Next, as we move away from the center towards the surface, is a level called the radiative zone. So this is the shell that borders the core but extends up significantly towards the surface. You can see it labeled in the figure, and it's where all the wiggly lines are passing through, and it covers this whole kind of gradient of colors, with the core just being at the very center. The energy within the radiative zone travels as electromagnetic radiation outward from the core. Very high energy photons are converted to many low energy photons. So the mechanism of heat flow in the radiative zone is radiation. And this is quite strange, because if you think about the mechanism of heat flow through solids, 9 out of 10 times we're going to tell you it's conduction. That's how the hot handle, the metal handle on a pan gets hot, right? The heat conducts through the metal, and that's how heat is going to flow through the rock of the mantle of Earth from our molten core. It's going to flow up towards the surface through, actual convection, rising of hot fluids, hot magma, but also conduction through the rock, right? That mechanism of just heat moving through a solid. But that's not mentioned here. And that's because the pressure is so great that conduction doesn't really work well under really high pressure. It's almost like the pressure is pushing back against the vibrations that are part of this, kind of the explanation of conduction. Conduction is almost like this chain reaction of absolutely mechanical vibration. That's that's on the fundamental level what's going on. Don't worry about it too much if that doesn't make sense, if you haven't seen conduction explained before. We're not trying to explain it in depth here. I'm not trying to explain it in depth. But suffice to say, this really high density level, which is indeed, you can look at your density measurement here, where the radiative zone, starts with a density equal to gold and gradually becomes less dense than water. Well, what's happening is it's behaving more like glass. Because yes, you can absolutely have, warm up a piece of glass, but the way that at least visible light energy passes through glass is through transparency. The photons actually go through that glass. They get picked up by one molecule in the glass and then passed on to the next through absorption and re-emission. Remember those terms: absorption, emission, excitation of electrons. So it's this reaction of just like kicking that photon forward. And that's what's happening inside the radiative zone, is it's behaving like a really thick sheet of glass, and essentially following the rules of transparency for light. Not visible light in this case, but rather starting at gamma rays and gradually decreasing in energy per photon, increasing in wavelength, and decreasing in frequency, until finally the density and pressure becomes sufficiently low that a new zone becomes possible. And this is the uppermost of the interior zones of the sun. So now we have a point where the sun is able to move like a fluid. Now it's actually able to wiggle, and it's able to, most importantly, to follow the physical laws of convection. And convection is the bulk movement of fluids. It's the idea that hot air rises and then becomes less dense as it does so, until the expansion allows for the dissipation of the energy that facilitated the rise in the first place. And that means that now your fluid, which is cooler and less dense, will sink back down and thus allow the process to start all over again. So convection is all about cycles of rising and sinking. And if you look at the picture, you can see little circles representing those convection zones and that cyclic process. Hot, rise, cool, and sink. The temperatures, which I hadn't called into focus too much when we talked about the radiative zone, but had decreased to a modest 1 million Kelvin, fall off gradually at first, and then precipitously towards the very surface of the sun, which we are now going to be hitting the photosphere next. And when we do, of course, we're going to hit a range of temperatures on our logarithmic axis that are going to be on the 1,000 scale, because that's where we're going to find 5,800, which indeed is this order of magnitude, or this power of 10. The densities also fall off gradually at first and then quite dramatically at the end. The convection zone has that energy that travels as convection cells. Cells are what is the name given to each of these sort of closed loops, also sometimes called zones, as the figure shows. The notion of convection cells is the same as rising magma and sinking magma that happens beneath mid-ocean ridges on Earth, and is the driving mechanism of our plate tectonics. We see the convection currents within the magma. We also have convection in our atmosphere. And we'll study more about the interior and when we talk about this content in chapter 16, but it actually won't be next week, because it'll be tomorrow. Okay, well, we're done with the interior for now. As I said, just a quick overview. Let's move on to the surface of the sun. We'll talk a bit more about the surface and the atmosphere in this chapter, because that's kind of the focus. So the surface of the sun is the part we can see. Okay, so the photosphere, like you see a photo, this is the part you can see. So that's kind of the mnemonic device that people use, is that the photosphere is the part you can see. That temperature is 5,800 Kelvin. That applies to that peak wavelength. If you remember your black body curves, this sort of sets the color of the sun, at least the color of the most probable photon that's released. Remember the homework where we talked about a cooler star and the most probable photon that was released from it, and how that compares to the sun. Also, this sets the middle of the rainbow. So 5,800 Kelvin corresponds to a wavelength that's going to be in the middle of the rainbow, because that curve of black body radiation is more or less symmetric, especially within the center of the curve. Obviously, the tails are more lopsided, and that's the notion of why it matters, right? It tells us that, the sun produces quote unquote white light because that's what we think of it as, right? It's the light that we can see, that we evolved to see, because it's the light from the sun. So getting back to the notion of the photosphere and what it is, we can't see material below the photosphere because of the density. The density of the material there is what? So take a minute, make sure you understand this, and give me your answer. Why can't we see below the photosphere? Okay. All right, so far, Maxwell says 3, Kylie says 1. Let's see, I'll run with that. 2 votes. It does turn out to be 1. So both of you agree that it's too high, that the high density is what matters, and it is the too high to allow the light to escape. Because what do we see, right? We can't see into dense things because the light is there, right? But it's bouncing, these atomic distances and just, getting reabsorbed. And we can't tell that's happening. We can only tell once it once that solid object borders a, something like air or the vacuum of space, and now we can see the emission from the boundary. So it's the too high to allow light to escape. And that notion we will come back to quite a bit, that when we talk about things being opaque, it's really about the escape of light. And if something is too dense, the light is trapped. This will matter in particular at one of the last chapters we cover, when we talk about the Big Bang and a very fascinating signal from the Big Bang called the cosmic microwave background radiation, which was the first thing that ever made it out of the primordial universe once the universe's density fell sufficiently low to allow for light to escape. See the commonality. What is the structure of the photosphere? What happens when we zoom in on it and take a closer look? Well, we notice all kinds of granulation. So we see this pattern that looks like maybe grains of something, looks like all of these separate little like spots, this pattern of mottled dots, all sort of, various shapes. And the term that's given to this particular surface feature, which is pretty universal throughout all over the photosphere, is called granulation. And it's because it's grains, right? Our figure here kind of shows a hint, shows a zoom in box pointing to the granules and calling your attention to the convection zones. So with that in mind, go ahead and answer this question. Dark edges appear around or between, depending how you think about it, granules because in the dark regions, hot material is rising, hot material is sinking, so it has something to do with convection, cooler material is rising or cooler material is sinking. So what makes the dark spots? Which of these four? What do you think it is? Okay, we got a hotter material that's sinking, cooler material that's rising. Hotter material that's sinking. Are you sure? Because hot material wouldn't sink. Remember, convection involves hot things rising. With convection, it's hot that rises. Okay, that's the hot. And once it rises, it loses its heat in order to expand. And then, which just happens naturally, and then once it has used up all that heat to facilitate its expansion, then it now sinks as a cool material. So if it's sinking, it has to be cool. If it's rising, it has to be hot. So that means that 2 and 3 are out because they violate that rule. Okay? But hey, no worries. That's it. That's the, we're learning this. So I wanted to hopefully make it clear. Yeah. Okay, so this is just showing the granule and now, really spelling out, okay, right? Dark spot, sinking. What's sinking? The cooler material. By the way, the material, I think one of the slides does say this in just a moment, but the material is plasma. What that means is it's an ionized gas. So there's so much energy in the sun that not only are there not molecules, this is a nice tie-in with that question we saw a few minutes ago, but there's also not any electrons around atoms. There's too much energy for atoms to hold on to their electrons. So all of the atoms have had their electrons stripped away, and that process is called ionization. So we say that all of the atoms are ionized, all the hydrogen, helium, and everything else. So when we talk about the material, it's a gas, right? Due to its properties of density and the way it can fill in volumes, rather than having a fixed volume, which would make it a liquid. So it's a gas. But since it's an ionized gas, it's a plasma. So plasma is like basically a subcategory of gas, but also sometimes described as a fourth state of matter, only in the sense that it's just a higher energy And if you can, of course, keep going and then have, even further high energy processes like fusion and fission. But getting back to convection, gas at the edges of the granules is sinking back into the sun, and that's the cooled gas. Okay, this one I'll give you a chance to think about, but I'm gonna do it too quickly to check your answers. Gas at the edges of the granules are sinking back into the sun, as we know. Compared to the gas that was not moving, this gas will show blank wavelengths in its spectrum. Okay, so in other words, I compared to the gas that is kind of at a stasis point that is neither rising or sinking. What would we be able to say about the wavelength of the sinking gas? Okay, so what's the logic here? Well, it's cooler. Okay, so if it's cooler, what does that mean for wavelength? Well, cooler means longer wavelength. Okay, so cooler means longer lambda. Because remember, lambda is the letter that we use for wavelength, that weird Greek letter right there. So that means that's the direct association. Cooler, because it's sinking, at least that's one way to think about it, and therefore longer wavelength. Okay, so photosphere, 5,800. Next, what's above the photosphere? So now we're moving into the solar atmosphere. And the very next level, you could think of this as the lower atmosphere. The equivalent on Earth would be the troposphere. This is the lowest part of Earth's atmosphere. Well, on the sun, it's called the chromosphere. So chromo, like color. It's a thin, hot region that is glowing red hot from excited hydrogen. So H alpha, or hydrogen alpha, is an excited state of hydrogen. And it is too dim to be visible. We don't see it. We don't see some glowing like halo around the sun. We just see the sun as a disk, right? Without a blurry edge or anything. The only time that it's visible is during a solar eclipse, because then the photosphere is blocked and all of its brighter light is obscured, allowing for the dimmer chromosphere to become visible. Okay, so the chromosphere is just too dim to otherwise see. Its intensity is too low because there's too few atoms actually creating the signal. And the intensity is related to, to how many carriers you have for that signal. All right, so looking at the level, so the idea here is that this is showing the photosphere and the chromosphere from kind of a side view. And here they are labeled, chromosphere, photosphere. So now another great question that, actually, like the one that I just gave away a minute ago or didn't check answers for, is really a nice tie-in with chapter 5, which is actually a totally important statement, is that a lot of the content in this chapter relies on what we saw in chapter 5. In other words, we're really putting to use the foundational ideas that we saw in chapter 5. If you don't recall, chapter 5 was the chapter where we talked about light. We really kind of, did a crash course on the physics of light. And now, of course, with our light source, the sun, we're going to be really relying on that. So that means we're going to be talking about, black body radiation, as I already have been, and types of spectra. Remember, there's 3 types. So let's identify what the photosphere and the chromosphere, which type of spectra they produce. So looking at the photosphere, we see blank spectrum. Looking at the chromosphere, we see blank spectrum. So what word should go here in order? Should it be absorption and then continuous? Absorption and emission? Continuous and emission? Emission and absorption? Or emission and continuous? So what would be the correct? The first one corresponds to photosphere, second one to chromosphere. So which of these options is right? Okay, so let's see. Okay, so far 5, 2, 3, 5. Okay, cool. Well, Kylie, you made a good adjustment to your answer there, and you nailed it. Well done. And I can see that this one definitely made a lot of you think, and you weren't sure on your answer, I'm guessing, or you weren't, you mixed up some of the definitions of the different types of spectra. We won't do a full review right now of them, but if you go back, you can look at, how these different spectra were described. I will try to at least make it as clear as I can in a short amount of time. So the reason that it's continuous in emission, okay, the kind of the best way to just hit the key idea here is that the photosphere corresponds to the temperature. We talked about that a lot, right? Photosphere has a temperature of 5,800. Well, if you see any mention of temperature, then you should probably think continuous spectra. I mean, it's a bit of a mental shortcut, but it's really never going to fail you. Because if we're talking about temperature, we're talking about a continuous spectrum. Because otherwise, yeah, sure, like some thin gas that just has an emission or absorption spectrum, it has some defined temperature, but unless we're going to be quantifying it with its, with some sort of continuous spectrum, some other mechanism, we don't care. So temperature in the context of astronomy is just totally related to continuous spectrums because that's the black body. And maybe the most tricky part is the way there's the synonyms, right? Because sometimes we call it black body radiation, sometimes we call it continuous spectrum, but they mean the same thing. So black body radiation, continuous spectrum, two terms for the same thing. Okay, so the fact that there is temp means that the photosphere has to be continuous. The chromosphere, it wasn't obvious. If you by some random chance knew what the heck hydrogen alpha was, which I kind of briefly explained, but I was trying not to give it away, then maybe you could think, oh, well, hydrogen alpha is an excited gas, right? Well, as I kind of, mentioned in passing, right? Well, excited gas doesn't imply cool gas, does it, right? Excited gas means like glowing, like a neon sign glows. That's how neon signs glow. You have excited gases trapped in tubes. So if it's an excited gas, that means it's emitting light rather than absorbing light, which is what cool gases do. So that, we can kind of then reason out, okay, well then maybe the chromosphere is an emission spectrum, and indeed it is. That color, that reddish color that we see from it when we can see it is its emission. The emission that happens because the excited atoms eventually relax, and when they do, they emit a photon, they emit light. But also the answers here were set up in such a way that only 3 had continuous spectrum first. So if you knew that, that was sufficient. Okay, so hopefully that is a good review. Next in the atmosphere is the transition zone. This is just a narrow region where the temperature rapidly starts to rise. We go from the atmosphere being cool at first, but then, already becoming hotter when we were in the chromosphere, but then becoming much, much hotter. And then we reach the corona, which is a very, 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 very thin layer, low density, in other words, that stretches out past Saturn, although most of it is well within the orbit of Venus, and most of it is even closer. So don't get too bogged down by thinking that it goes out that far, right? It's just, the very edges of this, really kind of the solar wind at that point. But anyway, of strongly atomized atoms that produce weird emission spectra, right? Weird. But what do I want you to really focus on is the high temperature is one thing. And don't think that that is totally crazy, because although it might seem weird that now we're going away from the sun and the temperature suddenly jumps up, it really just goes hand in hand with the fact that the density has fallen off so much. So we have just a few atoms that are absorbing some really high energy light that's coming from the sun, and therefore being allowed to vibrate very quickly. But there's not much heat in the corona because there's too few atoms to make it hot, right? It's just high temperature, because those are very separate ideas. And we even see that with our own atmosphere. If you go to the upper atmosphere, the temperature is really hot because of X-ray absorption. The X-ray is coming from the sun. but you wouldn't feel hot if you were up 200 kilometers or 150 kilometers above the Earth, and you put on a breathing mask but took off your insulated suit, because you start to freeze, and because there's too few atoms to actually warm you up. Even though each atom is really hot, thousands of degrees Kelvin, you know, they don't feel hot because there's just too few of them to actually collide with your skin. So, that's what I mean by like not being hot, but still being high temperature. And that is the similar idea of the corona. It's absorbing some very high energy light, that's coming from the sun, but due to its low density, it doesn't actually contain a lot of heat. But since it is so hot, when it does emit light very faintly, it's going to emit it in the X-rays. So the corona has a lot of X-ray emissions as well as X-ray absorption. And so that's got the process of the corona is a high temperature gas, kind of like the chromosphere, but even higher temperature, but just a very low density, so very faint signal. Here it is shown in a artificially colored image with the X-ray emissions being represented. The solar wind starts within the corona and extends out past it, and it is the flow of protons and electrons from the sun. If you remember the solar wind, we talked about it when we talked about how it interacts with magnetic fields, how it causes the auroras on Earth, how it causes auroras on Jupiter, for example, and how if you don't have a magnetic field, then the solar wind will just hit a planet dead on. So why study the sun? In addition to it being close, it also creates the solar wind, and the corona extends far into the solar system, which means that it can affect us. Not so much on the surface of Earth, for the reason already mentioned, because we have a magnetic field and thus a dense atmosphere, and the two go hand in hand to kind of keep us away from that potentially harmful solar wind. But for space exploration or things that are near the poles on Earth, we care about the sun because it can directly affect us. So we will get to that idea of kind of solar weather and solar storms and what that means and kind of a quick summary of it. But before we do so, we want to introduce something called the sunspot and solar cycle. Because if we're going to be talking about, a concern about, the impact of the solar wind and coronal effects, then we might want to know, is there a way to predict it? In the same way that we can predict weather with seasons or even events that transcend individual seasons, like the El Nino and El Niña events in the Pacific Ocean, right? Those all involve cycles. Well, there is a cycle in the sun as well that allows us to anticipate when the biggest solar storms are going to happen. And it turns out that cycle is directly related to the visible manifestation of it, which are the sunspots. So the sunspots are these blemishes that occur on the surface of the sun that follow this cycle that we're starting to discuss and increase in number over the cycle, hit minima at regular intervals, and are directly related to an important feature of the sun, the same physical mechanism that protects us from the solar wind, interestingly. And I know we're low on time, so I just want to do a couple more slides here. So just a quick definition, because I'm trying to relate ideas, but I don't want to miss, actually just clearly defining what a sunspot is. It is at an observational level, a dark spot that moves across the surface of the sun. Okay, so it's shown here. That's what these are. These are sunspots. They're regularly seen on the sun, quite easy to see, and have been seen historically for hundreds of years. And they look like this. Okay, just dark spots, usually in clusters that move across the sun. They don't really stay in place. They move gradually at a rate of a few, like kind of like if you track them over hours, you would notice a change. Why do they appear dark? Notice this is a similar question to why the edges of granules appear dark. Oh, and if you're wondering why this image doesn't show granules, it's just sort of the way that it's been processed and the particular wavelengths that are being shown. They're still there, but our focus is on the sunspots. The sunspots would cover, maybe a dozen granules typically in size. But anyway, so going back to why they appear dark. Are they just not giving off light? Are they just, completely no continuous spectrum? Is the light being absorbed by a magnetic field? Okay, so mention of a magnetic field, take note of that. Is there an object passing in front of the sun? Are they the shadow of something? Is the light being absorbed in an outer layer, maybe one of those atmospheric layers we talked about? Are they cooler than the surroundings, like the edges of the granules were cooler? What do you think? You get a quick answer before we wrap up today. Got 1 minute left. Hey, okay, thank you, Maria. Awesome. And you know what? We're low on time, so what? Yeah, I was going to say you were right already, but then Maxwell came in with the right answer. To be doubly right. Collectively, Jacob, nice job. They are cooler. So it's just the same logic, right? Cooler is darker because why is cooler darker? Well, if you remember, it's that black body spectrum, kind of like the light is moving out of the visible. So if your peak wavelength is in infrared, well, that means that it looks darker because now the human eye isn't able to see it as well. So that's what makes it darker, is that idea that the wavelength has moved out of the visible spectrum. If you're wondering in the back of your mind, like, wait, is that really obvious that darker is cooler? Well, the reason is because of the peak wavelength. All right. Cool. Yeah. Woohoo indeed. Nice job. All right. And that is a pretty good stopping point, especially because here's the two examples of the spectrum I've been talking about so much, which will be a great tie-in to get us started. We made it through most of the lecture on chapter 15. We just have a little bit of this sunspot cycle to wrap up. Make sure that it's going to be clear that it's related to the magnetic field, the sun's magnetic field, because just like Earth and the Jovian planets, the sun has a magnetic field. And then finally finish up with a few slides of that solar weather I hinted at. So those are all things you can look at ahead of time if you'd like to, but otherwise we'll cover it tomorrow, and there'll be a Canvas quiz on this material.